Hello guys, welcome back to another video. Today we're going to be discussing AP Physics 1, or it's going to be my very first video on physics. And we're going to be covering kinematics, everything you need to know about kinematics, the key components, just some key information. We're not going to go over everything in kinematics, but again, the key stuff that I really think you guys should know and get down. All right, so the very first thing I wanted to cover are scalar and vector quantities. So what does it mean by a scalar quantity or a vector quantity? So a scalar quantity can be any value, such as time, distance, as you can see on the graph that I have, time, distance, mass, speed, area, volume, and so on. So what a scalar quantity means is that it has no direction, but it does have magnitude. So if you see this like arrow here, basically that is a vector quantity because of course from one tail to its head, it has a certain magnitude, it has a certain length, and then it also has a direction. It has the arrow pointing towards, um, I guess that would be the east, something like that. But again, it has a direction and magnitude. Now, what are examples of vector quantities? That could be displacement, velocity, acceleration, force, weight, torque, momentum, electric field. But keep in mind that scalar quantities such as time, for example, well, it only has a value, such as 1 second, 2 seconds, a minute, 2 minutes, but it has no direction. Time cannot have any direction. So therefore, it is a scalar quantity. But vector quantities such as velocity has both a magnitude, a certain amount, but also does have direction. You're going north, south, and negative, positive. That could be examples of direction or signifying direction. And then the next thing I want to cover, now let me move my camera there, is position, velocity, and acceleration. Those are three key aspects of kinematics that you guys will cover in Physics 1. So as you can see here, first I want to cover the formulas that I have listed as 1, 2, and 3. So those are your common formulas for kinematics. So the V here is technically known as velocity final, is equivalent to your velocity initial plus your acceleration times the time. And then in formula 2, we have your displacement is equivalent to your position at initial position plus velocity initial times the time plus 1/2 of your acceleration times the time is squared. And then your third formula, velocity final squared, is equivalent to your velocity initial squared plus 2 times your acceleration. And then in the parentheses, we have your final displacement minus your initial displacement. So those are your formulas. I just wanted to show you guys or go over what each basically variable meant. But when you're learning, of course, physics in your own classroom, this will become more clear. And then if you see on the graph that I have on the left, I am showing a position versus time graph. So I want to analyze the position versus time graph in relation to a velocity graph. So for example, if you see that just that flat line where it says not moving, the position is constant. Well, of course, if your position is constant, you're not moving at any certain velocity. So your velocity is 0 from this time to this time. That could be like 1 second. And then you see that you are increasing in position. It's like a steeper slope, of course. And for example, that could be from time 1 to 2 seconds. You are moving with a positive velocity. You are moving, right? Your position is changing over time. And then from here to here, you're moving with negative velocity because your position is decreasing. You're going back. You're going backwards, essentially. And then I want to go over this diagram I have here, velocity as well as acceleration. So this is kind of confusing, but with velocity is equivalent to the change in displacement over the change in time. So if you see that delta S, that's just basically displacement, but it's not technically this distance. I originally thought that it was distance, but technically it's displacement, and for one reason, because velocity has direction. Displacement also has direction, but distance is a scalar quantity. It has no direction. It has no association with direction whatsoever. So that's why it's changing displacement, but you can also use the change in distance as well. But keep in mind that if you're writing the velocity formula out in terms of change in displacement or anything like that, keep in mind that it's displacement over time. And then acceleration is just a change in velocity over the change in time. And I want to make something very clear here that, if you're ever doing any operation with any of the formulas in physics, another way you can check whether you have the right value is by looking at the units. So, for example, velocity. So you can see here that it's change in displacement over change in time. Displacement, its value is in meters, right? And then your time is in seconds. Well, meters over seconds, that's meters per second. Velocity is in meters per second. So the units match up, so that makes sense. And then acceleration, your velocity is in meters per second. Divide that by the time, which is in seconds. That's meters per second, or meters per second squared. So basically that makes sense. It makes sense for your change in velocity to be over the change in time because the units will become meters per second squared, which is equivalent to acceleration. Okay, there we go. And then I want to also go over like the position, velocity, acceleration in terms of graphs. I want to take this another step and go over it. So if you see here that this position graph, it's this exponential kind of a graph here, half of a parabola. If you were to split this and have another part of the parabola on the left side. But the key component here is that you see that if the position is exponential, its velocity is just this linear graph, and then acceleration is just this flat line. Why is that? When you are translating a position to velocity or velocity to acceleration, you always look at the tangent line or the slope at any point. So what I mean, let's take this step by step. So let's say, for example, this is at time 1, and then you want to take the slope of the graph at this point. Okay, we have that. But then if you take the slope of the graph or the tangent line at this point, it has a greater slope value. So let's take this again. Let's do this again, essentially. At this point, we have a slope value of the graph. If we take the tangent line, we have a slope value of this graph of this point at this tangent line. And then we have another slope value if you go up here, for example. But each time you're taking the tangent line and taking the slope of that line, it's increasing. The slope is always increasing. And that is why if we translate it to the velocity, your velocity is basically increasing at each point. At this point, your velocity has a greater value. At this point, your velocity has a greater value. So if you're going from one level to the next, you always have to look at the tangent line and its slope value. Kind of like the derivative. Velocity is the derivative of position. Acceleration is the derivative of velocity. That's how it works. And it's actually pretty cool how you can associate that with derivatives, but that is another way you can think about it. And then acceleration, for example, well, velocity has a constant slope value, right? According to this graph. So for example, at this point, it has a constant slope value. The slope doesn't change. At this point, same slope. And that's why if we translate this velocity graph to an acceleration graph, it's just going to be a flat line. It's going to be a constant acceleration. So that was just an overview of a couple of things that you should know about AP Physics 1 in terms of kinematics. We're going to go over to the whiteboard now, do an example, but hopefully this all made sense, at least a little bit. But again, if you guys have any other questions, please contact me or post anything in the comments and I'll be more than happy to help you guys out with that. So, but now we're going to head to the whiteboard and do a quick example with the formulas in kinematics. See you there. So of course, we're going to go over the example, and then to the left of the example, as you can see, I have 3 of the formulas that we commonly use in kinematics. So we're going to read the example, break it down, and we're going to discover, well, which formula is best to use, and we'll plug and chug the values in to get our last desired value. So the very first thing we should do is, of course, read the example. So let's do that. It says, an engineer is designing the runway for an airport. Of the planes that will use the airport, the lowest acceleration rate is likely to be 3 meters per second squared. The takeoff speed for this plane will be 65 meters per second. And then assuming this minimum acceleration, what is the minimum allowed length? Okay, so there are three things we have. We have the acceleration, we have our final velocity, which is our takeoff velocity, and then we also have the desired value, which is the length of the runway. All right, so if we look at our first formula, we have acceleration, we have final velocity, initial velocity. We also have acceleration on the second formula and acceleration on this third formula. So let's take this down step by step. So we have acceleration in our given example, and I underline acceleration in all the three formulas. But how about our final velocity? Well, we have final velocity here. We also have it here. And, but we don't have it in the distance displacement formula. So we can kind of just get rid of that because it's given that we already have our final velocity value, but that formula does not accommodate the 65 meters per second. So let me just get rid of that and make. All right. And then what will distinguish between whether we're going to use this formula or this formula will be the desired value. So what does the desired value want from us? It's the length for the runway. So do we have any value that pertains to meters or displacement or distance? Well, this formula, no, it has only final velocity, initial velocity, acceleration, and time. But in this formula, we have final velocity squared, initial velocity squared, 2 times the acceleration, and we have final displacement and initial displacement. There we go. We have our formula. We have everything we need to really plug in everything into this formula in order to get our length of the runway. In this formula, no, we don't. We don't have, for example, the time. If we don't have time, we can never even use this formula at all because that's a key component. So let me delete that. And then, but you're probably wondering, yeah, so we want the displacement, right? But what about this like initial displacement or this initial velocity? Well, those are going to be 0 because this plane hasn't actually flown yet. Basically, the initial velocity will be 0 and the initial displacement will be 0 because it has not actually moved in a sense. So we can call these initial values 0. So our simplified formula essentially would be Vf is squared is equivalent to 2a and then x, or our final displacement basically. So if we basically plug in all the values here, so we have 65 meters per second. So let me draw an arrow here. So we have 65 meters per second squared is equivalent to 2 times 3, and then we don't have our final displacement. That's what we want. We want the length of the runway. So that's just going to be x. Awesome. All we need to solve for is just x now. So 65 squared is a big number for 4,225 is equivalent to 3 times 2, which is 6x. So divide by 6, divide by 6, and then you get x is equal to, and 4,225 divided by 6 is roughly 704.2 meters. And that is your final answer. Yeah, okay. So basically, when you want to solve a kinematics problem, take the problem step by step. Underline, box, do whatever you want, annotate the problem in terms of values that are given to you, and then look at the formulas on your reference sheet and see which one is best to use depending on which ones are given to you. And keep in mind that you can use multiple formulas on the reference sheet. It doesn't have to be like one formula that we used here. It could be depending on the problem. You could use equation 1 or one or the other. So keep in mind that it's not just one formula that you will have to use. It can be multiple. But the main idea here is that break down the problem, break down what you have given, and then according to the formula that you think will best accommodate your given values, use that, and then you will get your desired value. And make sure to check it too. Make sure it makes sense as well. Um, Make sure the values that you get make sense, that it's corresponding to your given value. We have 704.2 meters, so that makes sense in terms of the length of the runway. So that is the correct answer. So I hope you guys enjoyed this part of the video as well. I hope it makes sense. Hope you guys got an insight into how to approach these problems. And again, if you guys have any other questions, please let me know. And I will see you in the next video. Thank you so much.